So let us welcome in next lecture of MAT-401, that is numerical analysis. So this is last topic of the chapter, that is solution of system of linear equations. So today we will see the eigenvalue problem. So let A be the square matrix of order n with elements aij. We wish to find column vector x and constant lambda such that Ax equal to lambda x. So this x and this lambda should satisfy this equation. A is any square matrix of order m cross m and having elements aij. So matrix A just a minute. Yeah. The eigenvector corresponding to a lambda. So if x and lambda satisfy this equation, x equal to lambda x, then this x is called, see, x is called eigenvector, and this lambda is called eigenvalue. So this is the definition of eigenvector and eigenvalue. So this is our objective. So we find eigenvector corresponding to eigenvalue for given matrix. It may be n cross n, it may be 2 cross 2, it may be 3 cross 3, but it's general matrix. It may be n cross n matrix. So now x equal to lambda x, so this equation we can write as x minus lambda x. So A is the n cross n matrix. So here we can write lambda x as lambda ix. So I is identity matrix. So you can write I as, it is again n cross n matrix. So it is 1 0 0, it goes to 0, then 0 1 0. All diagonal entries are unity and all. So other than diagonal entries, all are 0. Top to that is 0 0, it goes to 1. So this is identity matrix I. So I, it can be written in this form. So if we multiply this I by lambda, so you can make this operation significant, that is A minus lambda I, which is multiplied by x equal to 0. So A is n cross n matrix, x is n cross 1 matrix. So you cannot make this operation. So this is not correct way to write this. So I should be there. So you can write I here, or you can write I here. So I should write this I between, yeah. So it is lambda ix. This is proper way. Otherwise, you cannot make this operation. So here, A into x, A is n cross n matrix, x is n cross 1 matrix, so resulting matrix is n cross 1. It is again n cross 1 matrix. So this equation is correct. But this equation should be in this way. That is Ax equal to. So again, what is Ax? See here. So A is a n cross 1 matrix. X, it is n cross 1 matrix. So resulting is n cross 1 matrix. So what is lambda ix? So I is n cross n matrix and x is n cross 1 matrix. So resulting matrix will be n cross 1. And if you multiply it by lambda, so what will be resulting matrix? So we can perform these operations. So this is the correct way. So resulting equation, we write A minus lambda I, which is multiplied by x equal to 0. So here, what is A? So A is, already we have written, So A, it is Aij, and it is n cross n matrix. So for I varies from 1 to n, and j varies from 1 to n. So we can write this matrix uh, in the matrix form. Sorry. So what is first row? For I equal to 1, so let us vary j. J varies from 1 to n. So you'll get first row. So A 1j, then A2j, A3j, and then ANJ. So these n rows are there. So A11, A1 top to A1n, then A21, A2 top to A2n, that is second row. Third row, that is A31, A32 top to A3n, and nth row, that is AN1, AN2 top to ANN. So this is matrix A. This is n cross 1 vector matrix. It is vector matrix. X1 is top to Xn, and that is equal to lambda x. So we just write this equation, that is Ax equal to lambda x. We write here the value of A, value of X only. See, so resulting system looks like this. So here, yeah, so you can transfer the terms on right side to left hand side. So what will be resulting equation? So matrix A, so this is vector x and minus lambda into I. So this is I matrix, this is X matrix, it is again X matrix, and this is A matrix. So X minus lambda Ix. So which already I have written here. Yeah, I'm just simplifying this, and what will be resulting. So you can multiply this matrices. So it is n cross n matrix, it is n cross 1 matrix. So it is again n cross n matrix, and it is n cross 1 matrix. So what is the resulting product of these two matrices? It will be n cross 1 matrix, and again product of these two matrices will be n cross 1 matrix. So what is subtraction of resulting matrix? So resulting matrix will be n cross 1 matrix, and it will be look like this. So after simplification, you will get the resulting matrix, that is A11 minus lambda x1. Yeah, it is 0 means it is 0 matrix. Yeah, sorry. Why should why I'm writing this? So I should write this in the way. Yeah. So you'll get the system of equations. So comparing these two n plus 1 matrices, so you'll get these equations. So first, that is A11 minus lambda into x1 plus A1 to x2 plus up to plus A1 in xn equal to 0. Then second equation, that is A21 x1 plus A22 minus lambda into x2 plus up to A2n into xn, that is equal to 0. And likewise, so nth equation will be an1 x1 plus a into x2 plus up to plus, that is an minus lambda into xn equal to 0. So this is system of linear equations in n variables, and n equations are there, which is homogeneous system of linear n linear equations and have non-trivial solution if and only. So this is the property of linear algebra. Yeah, known result of linear algebra. See, so x equal to 0. Otherwise, so it is not significant. So this system x equal to b has non-trivial solution if and only determinant of a is equal to 0. So this is one well-known result of linear algebra. So using that, so determinant of a minus lambda should be equal to 0. So hence, what is determinant of a minus lambda? So already you have written this matrix a minus lambda. So this is here. Yeah. So determinant of this matrix. Yeah. Sorry. What is that matrix? A minus lambda. So determinant of this matrix will be 0. So from that, so you'll get. So this equation is called a characteristic equation of matrix A, and that characteristic equation of matrix A will be polynomial equation of degree n in lambda. So if you simplify this determinant, so you'll get, because all these values a11, a12, a13 up to a1 n, likewise an1 up to an, all these values are known from matrix A, because matrix A is given. So from matrix A, just unknowns are lambda here. Yeah, values of lambda which we have to find. So if you simplify this determinant, so you'll get yeah, polynomial of degree n in lambda. So the polynomial being called the characteristic polynomial of A. So corresponding polynomial is called characteristic polynomial, and this equation, that is equation number 2, is called characteristic equation. Yeah, characteristic equation of matrix A and characteristic polynomial of A. So these two terms are here, and that is our next part. If the roots of this equation 2 be given by lambda n, so suppose lambda 1, lambda 2 up to lambda n, so these are the n roots of this polynomial equation. Then for each value of lambda n, so there exists corresponding xi, that is eigenvector xi, such that so it will satisfy uh, original equation, that is ax equal to lambda x. So it will satisfy xi equal to lambda xi. So here I varies from 1 to en. So it is there. The eigenvalues lambda n may be either distinct or repeated. Distinct means all are different, or maybe repeated means some may be equal. This set of all eigenvalues of lambda n of matrix A is called spectrum of A, and the largest of eigenvalue. Just a minute, what is problem? I'm missing this screen. Yeah. So what is spectrum of matrix A? This set of all eigenvalues of matrix A is called the spectrum of A, and the largest eigenvalue, largest mode of eigenvalue is called spectral radius of A. So these two terms are there. Maybe there will be an objective question on these two terms. What is spectrum and what is spectral radius of A? So next we will solve one problem in which we will find eigenvalues and eigenvectors for given matrix. So let us take A, which is matrix, so which is 3 cross 3 matrix. Suppose it is 5 0 1 0 minus 2 0 1 0 5. The characteristic equation of matrix A is given by, so already we have seen. So determinant of this matrix A minus lambda equal to 0. So this is the characteristic equation of matrix A. So I is identity matrix. So here matrix A, what is lambda? You can simplify this. So what is A minus lambda I here? So A, that is matrix, I'm just writing it. So it will be 5 0 1, that is 0 minus 2 0, that is 1 0 5, minus lambda times identity matrix. So here you have to take 3 cross 3 identity matrix. So it will be 1 0 0 0 1 0 0 0 1. So it will be a corresponding difference. So it will be 5 0 1 0 minus 2 0, it is 1 0 5. Then what is second matrix? It will be minus yeah, or you can write just lambda. Yeah, lambda 0 0 0 lambda 0, and that is 0 0 lambda. So if you take the difference of these two matrices, so it's nothing but, see, so it will be 5 minus lambda, then it is 0, then it is 1, then it is 0, then it is minus 2 minus lambda, then it is 0, then it is 1 0, and that is 5 minus lambda. So that will be A minus lambda matrix. So its determinant equal to 0, that is our characteristic equation. So we have to solve this, and then we will find the eigenvalues for given matrix A. So obviously this part is there. I'm not writing this part. Just a minute. Yeah. So this is the characteristic equation of a given matrix A. So you can write it as suppose equation number one, or you can simplify this. So after simplifying, you will get the characteristic equation. So this is characteristic polynomial of matrix A, of matrix A. See, so if you find the roots of this polynomial, so you'll get lambda 1 equal to minus 2. So what are the roots of this polynomial? So minus 2, 4 and 6. So you can write this polynomial as lambda plus 2 into lambda minus 4 into lambda minus 6, and that is equal to 0. So roots of this polynomial will be lambda 1 equal to minus 2, lambda 2 equal to 4, and lambda 3 equal to 6. So next we obtain the corresponding eigenvectors for these three distinct eigenvalues. So for eigenvalue lambda 1 equal to 2, so let us find eigenvector. So we'll find eigenvector x1. So let's suppose the eigenvector for eigenvalue lambda 1 equal to 2 be x1, x2, x3. So then we have, so it satisfies the original equation. So naturally we can write ax1 equal to lambda 1 x1. So let us put the values of a and lambda 1 here. So after substituting these values, so you can simplify, you can multiply these two matrices. So you'll get multiplying and comparing the corresponding elements. So you'll get these three equations, that is 5x1 plus x3 equal to minus 2x1, then minus 2x2 equal to minus 2x2, and then x1 plus 5x3 equal to minus 2x3. So which gives the equations. Let us see. So from equation number 1, so you'll get 7x1 plus x3 equal to 0. So you can transfer this term here to left hand side. So you'll get 7x1 plus x3 equal to 0. And from third, you'll get x1 plus 5x3. So you can transfer this minus 2x3 to left hand side. So you'll get x1 plus 7x3 equal to 0. And this solution is, so after solving these two equations for x1 and x3, so you'll get x1, x3 equal to 0 with x2 is arbitrary. So you cannot find the value of x2 here from these two equations. So from first and third, you'll find the value of x1 and x3. From 2, you can find the value of x2, but there is only x2. So how you can find? So it does not mean x2 is again 0. So arbitrary is arbitrary. In particular, we take x2 equal to 1 and the eigenvector is, that is 0, 1, 0. So yeah. So next we'll find the eigenvector corresponding to a second eigenvalue, that is lambda 2 equal to 4. Just a minute, there is some technical problem. I'm not able to share my OneNote screen. Just a minute. Yeah. So next we'll find the eigenvector corresponding to second eigenvalue, that is lambda 2 equal to 4. So let's suppose x2, so that is equal to x1, x2, x3 be eigenvector corresponding to eigenvalue lambda 2 equal to 4. So naturally it will satisfy the original equation, that is x equal to lambda x. So from that you will write x2 equal to lambda x2. So let us put the values of a and lambda. So naturally lambda 2 is here. Yeah. So it will use again. So by multiplying and comparing two matrices, so you will get equations x1 plus x3 equal to 0 and minus 6x2 equal to, so from which we obtain x1 equal to minus x3 from first and x2 equal to 0 from second. So in particular, we choose x1 is equal to, so this relation is there between x1 and x3, but both are arbitrary. So in particular, you can take x1 equal to 1 upon root 2, and so naturally that will imply x3 equal to minus 1 upon root 2, so that, so it will satisfy. So we are choosing x1 and x3 so that it will satisfy this equation, that is x1 square plus x2 square plus x is equal to 1. So that, so resulting eigenvector will be normalized eigenvector or normal eigenvector. So here the vector x2 can be written as, that is 1 upon root 2, 0 minus 1 upon root 2 is the normalized form of this eigenvector. So you can take one, any particular value for x1. So naturally x3 will be minus of x1. So corresponding eigenvector we'll write always in this form. This problem. Yeah. So next, eigenvector corresponding to third eigenvalue, that is lambda 3 equal to 6. So again, let's suppose x3 equal to x1, x2, x3 is the required eigenvector. So then it will satisfy this equation, that is x3 lambda 3. Just a minute. Yeah. Lambda 3 x3. So putting the values of a and lambda 3, you will get this equation. After multiplying and comparing the corresponding entries, so you will get the equations, that is minus x3, x1 plus x3 equal to 0, minus 8 x2 equal to 0, and x1 minus x3 equal to 0. So from first and third, you will get x1 equal to x3, and from 2, you will get x2 equal to 0. So from first and 2, you are just getting relation, but you are not getting the values of x1 and x3. These are the arbitrary. So choosing x1, x2 equal to 1 upon root 2, the resulting normalized vector is given by, that is x3 equal to 1 upon root 2, 0 and 1 upon root 2. So x1 equal to 0, 1, 0. x2 is equal to, that is 1 upon root 2, 0 minus 1 upon root 2, and x3 is equal to, that is 1 upon root 2, 0, 1 upon root 2. So these are the three eigenvectors corresponding to eigenvalues lambda 1, lambda 2, and lambda 3. That is minus 2, 4, and 6. So this is the end of this chapter. That is solution of a linear system of equations. So next, in next lecture, we will start next chapter. There is last chapter, solution of ordinary differential equations using numerical methods. So till then, so I will stop here. So due to some technical problem, I'm not able to share this screen. So I'll stop here.